I think ensemble prediction has enormous applications in other areas, and in the book which I wrote and is out now, I discuss applications of ensemble prediction to conflict, COVID, and indeed the economy. And it's a kind of fascination to me about whether these sorts of systems also have periods, and it seems that they do, periods of very high predictability interspersed with periods of extreme intermittent instability. And again, ensembles provide the means to predict that ahead of time and hopefully take precautionary action. Now, I'm not going to talk about this in this talk, but if you're interested, there's chapters in the book. Because what I want to finish with is the, 2021 was Suki Manabe. 2022 Nobel Prize were three physicists, Alain Aspect, John Clauser, and Anton Zeilinger, who did one of these quantum experiments, which, as I say, I would say is if you had to say one physics experiment which is just conceptually difficult to understand, it is this one. It's the so-called Bell experiment. I'm going to try and explain what I mean by that. And here's some sort of, so here's what the Scientific American said when they got the Nobel Prize. The universe is not locally real, and the Physics Nobel prize winners proved it. Here's some stuff I just pulled off YouTube. Einstein proved wrong. And the other one, scientists, who proved the universe is not real. Okay, so you might think that's bizarre, but this is what probably 99% of physicists believe. That these Bell experiments, I say what I mean by Bell experiments, the experiments that these three guys showed, independently, by the way, separate labs around the world, either mean that physics has what Einstein called spooky action at a distance, which means that something I do here, something I do in this lecture theatre, put this hand up rather than this hand up, can affect an outcome of an experiment potentially on the other side of the galaxy. So that's what spooky action at a distance means, and it sort of doesn't make a great deal of sense to many people, but nevertheless. Or we have to say that quantum reality somehow, is indeterminate. There's nothing definite about reality. And Einstein also coined the phrase to his dislike of, he coined the phrase spooky action at a distance because he didn't like that. And he also coined the phrase God doesn't play dice to sort of encapsulate his dislike of this notion of indeterminism. But now most people think Einstein was wrong, and Niels Bohr, his great advocate who argued quantum mechanics is weird, was right. But I want to show you there is another argument. But I need to do that. I need to say a little bit about this Bell experiment. So excuse perhaps a little bit of the detail, but I'll try and make it as simple as I can. The experiment is based on a source of pairs of particles, photons, let's say, particles of light. And these particles are what are called entangled. They have properties which are sort of correlated with each other. Now, in some way, that isn't a kind of a big deal. You could imagine a source spitting out a red ball in one direction and a blue ball in the other direction, and you say, well, okay, if I see that this is a red ball, I know the one over here is a blue ball. So the fact they're correlated isn't itself a problem, but we'll see the correlation is such that you can't explain it in that simple way. So we've got these two particles going out at kind of in opposite directions, and we have these kind of cartoon figures. They're called Alice and Bob experimenters, who measure the polarizations of these photons. They have polarizers which you set to a particular orientation. You can orientate your polarizer with respect to the stars in the sky or something like that. And the outcome of a particular experiment is that the photon is measured to have, a horizontal polarization or a vertical polarization. It comes out with one of two. Each experiment each individual realization of experiment comes up with like a 0 or a 1, a horizontal or vertical or up or down or something like that. So the way I'm going to describe this is that the experiment is run over 4 days, just for the sake of argument. And on each day, Monday, Tuesday, Wednesday, Thursday, Alice and Bob choose different orientations for their polarizers. They don't necessarily have to communicate. When they do the experiment, they don't communicate with each other which directions they're going to use. But Alice has 2 directions, and Bob has 2 directions. And I could call them the 0 direction and the 1 direction. So Alice has a 0 and a 1 direction. Bob has a 0 and a 1 direction for his polarizer. Okay, so Monday you have this little ensemble of entangled particles. Alice does her measurements, and she notes down when they get horizontal and when they get vertical, and similarly Bob. And then on Tuesday, they do the experiment again with another set of particles, but now Bob uses his second orientation. On Wednesday, they do experiments with a third set of particles. Now, Alice chooses a different orientation, and Bob goes back to the original one. And finally, on Thursday, they both choose the second of the pair of orientations. So each day, they have an ensemble of particles, and from those measurements, they can come together and basically calculate how well correlated the measurements were. So when Alice got a horizontal, did Bob get a horizontal? And when Alice got a vertical, how correlated were they? And this is an equation for these correlation coefficients, the 4 correlations. And it turns out, for a range of possible orientations, this particular mathematical sum and difference of correlations exceeds the value 2. And the reason why that's significant is that Bell himself, John Bell, showed that it's impossible for a traditional deterministic model to satisfy that inequality unless this notion of spooky action at a distance is occurring. So, in other words, how Alice chooses the orientation affects the outcome of Bob's measurement. That would be spooky action at a distance. Now, you might ask me, when I say traditional, what do I mean by traditional? So this is an important word which we'll come back to in a moment. But that is basically, so Clauser, Aspe, and Seilinger basically showed that experimentally, this correlation, that this sum and difference greater than 2, is really a very robust result. There's no doubt about that is what you see in experiments. So then the question is, how do you interpret that result? And most people, as I say, they take that last line, the bottom of the page, and say, okay, if it's a traditional deterministic model, then there must be spooky action at a distance, or the world isn't deterministic. There's something indeterministic, fuzzy, stochastic, noisy, there's nothing definite about anything. Now, this is where we're going to come back to fractals, because there's an implicit assumption, and it's very rarely mentioned when analyzing Bell's experiment. And I want to go through it sort of semi-carefully. Let's imagine, or let's consider, those particles that were actually measured on the Monday. Could those same particles have been measured with the polarizer settings on Tuesday, Wednesday, or Thursday's polarizer settings? Well, when you do a measurement on a particle, say 2 photons, they go into the polarizer, they kind of get destroyed. The photon gets absorbed by an atom, it kind of raises the energy level of an atom. That photon is gone. It's not there to do an experiment on Tuesday, Wednesday, or Thursday. So if you ask the question, could these same particles have been measured with Tuesday, Wednesday, or Thursday's polarizer settings, you're asking a counterfactual question, because it's not a question that could have happened. It's a question that perhaps might have happened. You might have said, well, suppose that particle, that photon that I measured on Monday, what would have happened if I'd measured that photon on the Tuesday instead? But that is a counterfactual question. And whether that counterfactual question has any meaning or not depends on the laws of physics. It can only depend on the laws of physics because you can't go out and actually do the experiment, because in reality, that photon had been measured and destroyed on the Monday. Now, the question then is it possible that one or more of these counterfactual worlds could be inconsistent with the laws of physics? If it was the case that the counterfactual worlds were inconsistent with the laws of physics, then you could actually explain Bell's experiment without having to invoke these incomprehensibly weird ideas about action at a distance or indefinite reality. So there is a literature, but it's not a well-known literature on Bell's theorem, which actually makes this point about counterfactual measurements, or the kind of well-definedness of counterfactual measurements are critical to the interpretation of this experiment. Okay, so here's what a physicist would say so far. Maybe there are some in the audience who are just dying to get up and say. They would say, yeah, but we use counterfactuals all the time. And they might cite an example. Suppose here's a boy. He's throwing the ball, the football, whatever it is, to his father. He launches the ball up. It goes through the air on a parabolic arc. The father catches it, all well and good. We might say, well, suppose the child had thrown the ball with half the initial velocity. Would it have reached the father? Well, that sort of question you can answer with your high school physics. You know, anyone who's done A-level physics or something, you know about projectiles. You have a formula which says, you know, for a certain initial velocity of the projectile and a certain angle, it goes on a parabola and it travels a certain distance over the ground and it hits the ground. So to answer that question, the counterfactual question, if the boy had thrown the ball with half the velocity, would it have reached the father? You just plug half the velocity into the formula and it comes out, you know, the distance is half or a quarter of the distance or something, and no, it wouldn't reach the father. So that is the traditional deterministic view. You have a formula. The formula covers what actually happened, and it covers all sorts of possibilities that might have happened but didn't happen. All possible counterfactual worlds. So the typical physicist response to what I've just said in the previous slide is, look, you're worrying about nothing, because clearly the laws of physics allow us to counterfactually vary initial variables and parameters and blah, blah, blah.